This is the video lesson for image formation in converging and diverging lenses. The learning target for this lesson is, I'm learning to apply the law of reflection to analyze image formation in converging and diverging lenses.
Success criteria for this lesson are, I can draw ray diagrams for converging and diverging lenses. I can determine the location and characteristics of the images created by converging and diverging lenses. I can determine if the images created by converging and diverging lenses are real or virtual. And I can use the lens equation to find focal length, object distance, and image distance. So what is a converging lens? So a converging lens converges light rays, or rays of light traveling parallel to its principal axis. So the rays of light traveling parallel to its principal axis converge on a point. So we have some important points on a converging lens. We have the principal axis, which is this line right here. We have the vertical axis, which is this line right here. This is in the middle of the lens itself, the vertical axis. We have the focal point. There's two focal points for each lens. Those are on either side of the lens itself. We have the focal length. So that's the distance from the vertical axis to the focal point, and that's on both sides of the lens. And then we have 2 times the focal length. So that is here marked 2f, and there's 2 of those. So that's the distance from the vertical axis to 2f. So that's 2 times the focal length. All right, what about a diverging lens? What is a diverging lens? So a diverging lens diverges rays of light traveling parallel to its principal axis. And again, for a diverging lens, we have some important bits of information. So we have the principal axis, which again is this line. We have the vertical axis, which is this line that splits the diverging lens in 2. We have the focal point, this point here, and that's on both sides of the lens. We have the focal length. That's the length from the vertical axis to the focal point. And then that length is on both sides of the lens. Then we have 2 times the focal length. So that is this distance here from 2f to the vertical axis. That's this distance. That's 2 times the focal length. All right, so just like we had rules of reflection for mirrors, we have rules of refraction for lenses. So there are 3 rules of refraction for converging lenses. The first rule says that any incident ray traveling parallel to the principal axis will refract through the lens and travel through the focal point on the opposite side of the lens. Okay, so here is our incident ray traveling parallel to the principal axis, and here it refracts through the focal point on the other side of the lens. That's rule number 1. Rule number 2 says that any incident ray traveling through the focal point, and this is the focal point of the lens itself on the object side, on the way to the lens so any incident ray traveling through the focal point on the way to the lens will refract through the lens and travel parallel to the principal axis. So that is this line here. So this line is traveling through the focal point. That's our incident ray. And then the refracted ray travels parallel to the principal axis. That's rule number 2. And then rule number 3, any incident ray traveling through the center of the lens will in effect continue in the same direction that it had when it entered the lens. So here is our ray traveling through the center of the lens, and it continues through the center. It just continues on that line after it goes through the lens. And so where those 3 lines converge, that is where our image is.
Okay, so we're going to draw the ray diagram for a converging lens. So this arrow with the this line with the arrows pointing up and down, this is a symbol for a converging lens. So we've got our object here. All right, so the first thing we draw is a ray that is parallel to the principal axis. Okay, then we draw a ray that goes through the focal point. Okay, and next we draw a ray that goes through the middle of the lens. So through the center, basically through the principal axis and through the vertical axis of the lens. Okay, so these are all incident rays. All right, and now we draw our refracted rays. So the refracted ray for the ray that goes through, that is parallel to the principal axis, goes through the focal point. The ray that goes through the middle of the lens just continues on. Okay, and then lastly we have the ray that goes through the focal point, goes parallel to the principal axis after the lens. Okay, and we want to know where these three lines converge. That is where the image is. So somewhere right around here is where our image is. So our image is inverted, and it's a real image because it is on the other side of the lens from the object. So here's our image. It's a real image, and it's inverted. And it's magnified.
All right, let's look at the three rules of refraction for diverging lenses. So any incident ray traveling parallel to the principal axis will refract through the lens and travel in a direction such that its extension will pass through the focal point. Okay, so we have our incident ray. So this ray diverges. So here's the diverging refracted ray, and it diverges such that it passes through the focal point of the lens. So here's the focal point, and here's our refracted ray diverging through the focal point. And here's the extension line going through the focal point. So number two, any incident ray traveling through the focal point on the way to the lens will refract through the lens and travel parallel to the principal axis. Now the trick to remember with diverging lenses is that the focal point is on the other side of the lens. So when we're drawing our incident ray traveling through the focal point, we've got to remember that it goes through the focal point on the other side of the lens. So here is our ray that goes through the focal point. And the refracted ray is parallel to the principal axis. And so we draw this extension that goes parallel to the principal axis. And then lastly, the third rule, any incident ray traveling through the center of the lens will in effect travel the same direction it had when it entered the lens. So this is the same rule as with diverging or converging lenses. So we have this ray traveling through the center. It's just going to continue on through the center. Now, same thing with converging lenses, where those three lines meet, that is where your image is.
Okay, now we're going to draw the ray diagram for a diverging lens. So we start by drawing a line parallel to the principal axis. So this is a ray parallel to the principal axis. Next we draw a line that goes through the focal point. So for a diverging lens, the ray that goes through the focal point goes through the focal point on the other side of the lens. The focal point on the side of the lens opposite the object. And then finally we have the ray that goes through the middle of the lens, through the line that meets the principal axis and the central axis of the lens. Okay, so now we're going to draw our refracted line, our refracted rays. So the refracted ray for the incident ray that is parallel to the principal axis diverges, and it goes through the focal point on the side of the lens with the object. So you can see it goes through the focal point on the side of the lens with the object. So this is our ray that goes to the lens, and this is our ray that goes through the lens. Then we have our ray that goes through the focal point. The refracted ray is parallel to the principal axis. We draw a dotted line, an extended ray on the other side, on the side with the object. And then finally we just continue this line, the ray that goes through the center of the lens, we just continue that line, that ray all the way through. So where these three rays meet, which is right here, that is where our image is. So you can see the image is upright. It's not inverted, but it is a virtual image because it's on the same side as the object. So in terms of lenses, what determines whether the object or the image is virtual or real is whether or not it's on the same side as the object or not. In the case of diverging lenses, the images are virtual because they're always on the same side of the lens as the object.
Okay, now we're going to talk about the lens equation. So the lens equation is identical to the mirror equation, except we're talking about lenses. So we have 1 over F equals 1 over DO plus 1 over DI. So F is equal to the focal length. DO is the distance to the object. And DI is the distance to the image. Okay, so now we're going to use the lens equation on a couple of examples. The first example deals with converging lenses. So we have an object is placed 37.2 centimeters from a converging lens that has a focal length of 25.1 centimeters. We want to know what is the distance to the image. So let's set up our equation here. So we have 1 over 25.1 centimeters is equal to 1 over 37.2 centimeters plus 1 over DI. So we'll do the math here on these to simplify. So we have 0.0398 is equal to 0.02688 plus 1 over di. So I'm going to subtract the 0.02688 from both sides. So we end up with 0.01296 is equal to 1 over di. So di is equal to 1 over 0.01296, which means that di is equal to 77.2 centimeters. So the image is located 77.2 centimeters from the lens. All right, let's do an example using the lens equation for diverging lenses. So we have an object is placed 79.4 centimeters to the left of a diverging lens. A virtual image is formed 20.4 centimeters to the left of the lens. Determine the focal length of the lens. Okay, so the one trick with diverging lens is to remember that the focal length is negative. So focal length is negative, and the image is also negative. So if we have a diverging lens here, we have focal length here and a focal length here. This is the focal length for a diverging lens. And it's negative. And the image, so let's say our object is here, object, and our image is going to be here, and this is the image, and it is also negative, and it's a virtual image. Okay, so with that information in mind, let's figure out our solution here. So we want to know the focal length. So we have 1 over f is equal to 1 over 79.4 minus 1 over 20.4. So we'll simplify. So we have 1 over f is equal to 0.01259 minus 0.04901. So we'll combine like terms. So we have 1 over f is equal to minus 0.0364. So then f is equal to minus 1 over 0.0364, which means that f is equal to minus 27.5 centimeters. So the focal length over here is at a distance of 27.5 centimeters. All right, everybody, keep asking questions. It's how you learn new things.